In Chapter 3, Section 10, we'll look at linear approximations and some differentials. So for the first problem, we have, well, let me set this up before we get to the first problem. So imagine we have a curve. So we have x and y, and we have some curve, let's say it looks like this. Well, imagine if we zoomed in on a chunk of this curve. So we are going to blow this up. Let's see if I can do this. So we're going to have this window be like this now. So this is going to map to here. This one's going to map to here, and this one's going to map to here, actually. Okay, then inside this window, this curve is going to look like this. And we imagine that any point on this curve, let's say right here, that can be approximated with a straight line. So you'll see that that straight orange line is really close to the blue curved line. And so what we say is the x component of that point is a, the y component of that point is the function evaluated when x is a, which we call f of a. And we're going to get a formula to find what's called the linearization of this line. So this orange line, let's see if I can write it in the space here, is we're going to say this is equal to y. So it has a function y equals, but we're going to call it L of x, the linearization of this curve at point x, is equal to the function evaluated at a plus the derivative of the function evaluated at a, which would be the slope of that tangent line, times x minus a. So this is just point slope form equation where we use the slope is the derivative, because we know the slope of any tangent line is the derivative evaluated at that x equal to a. Okay, so that's the idea. Now let's see this in action. So for the first problem, it says find a linearization of the function equal to the square root of x at a equal to 25. So we know the square root of x curve looks like this. And let's imagine we are at the point a equal to 25. Well, we know f of a is the square root of 25, which would be 5. So we are trying to find the equation of this line right there. Okay, so we're going to use our formula. The linearization of x is equal to the function evaluated at a plus the derivative of the function evaluated at a times x minus a. Now f of a is equal to the square root of a, which is 25, which is 5. But now we need the derivative. So the derivative of x, the derivative of the function with x as the variable, would be, let me write this slightly differently. This function is really x raised to the 1/2 power. And now we can use power rule for derivatives. The derivative would be bring the 1/2 down, then x, then subtract 1 from the power, so it's 1/2 minus 1, which would be 1/2 x to the minus 1/2, which is 1/2 square root x. So the minus half, that's a straight line, the minus half makes it a radical x, but in the denominator. We need to find that evaluated also at a. But a is 25, so it would be 1/2 2 times the square root of 25 which would equal 1 over 2 times 5, which would equal 1 over 10. So we know f of a, this value here, is 5. We know f prime of a, right here, this value is 1/10. And we know a is 25. And that's all the things we need to plug in. So the linearization of x is equal to 5 plus 1 over 10 times x minus 25. This is going to equal 5 plus 1/10 x, so distribute this 1/10 into both terms, minus 25 over 10. This is going to equal, let's write 5 over 10, which would be 50 over 10, minus 25 over 10, plus 1/10 x. This is going to equal positive 25 over 10, plus 1/10 x. 25 over 10, divide both numbers by 5, is 5 halves, plus 1 over 10x. And that's what I have here, 1 over 10x plus 5 halves. So that means that this line right here, if we were to extend it out, boy, I might have got this drawing just right. If we were to extend it out, its y-intercept is 5 halves, 2.5. And its slope, the rise over run value, you can see it runs a lot more than it rises. The rise over run value is 1 over 10. So it goes up 1 over 10. That describes that orange line. That is a linear approximation of the curved blue line at the point x equals 25. And that's the thing. These linearization equations change depending on the point you pick for your x value. Well, we call it the value for a. But it is an x value. Okay, so that's problem 1. That's pretty much what we're going to be doing, just more and more practice with that. Okay, let's look at problem 2. A little more involved, but still not too bad. They want us to find the linearization for g of x, and I'm going to write it a little differently than they have it. It's 1 plus x raised to the 1/5 power. And they want a to be 0. Okay, so first let's find the derivative. Power rule would say bring the 1/5 down, leave the parentheses the same, subtract 1 from the power. Then a lot of times we'll forget this, times the derivative of the parentheses stuff. So the derivative of 1 is 0, the derivative of 1x is 1. Okay, so if I do all of the simplifying for that, we'll get 1/5, 1 plus x to the minus 4/5, and then times 1, which doesn't change it at all. And I think you can just leave it like that for this problem. You don't have to worry about writing it in radical form. Okay, so that's the derivative. Now, we need both of these evaluated at a, which is 0. So g of 0 would be 1 plus 0 raised to the 1/5, which is just 1 raised to the 1/5, and 1 to any power is 1. So that one's pretty simple. G prime of 0 would be 1/5, 1 plus 0 raised to the minus 4/5, which is 1/5 times 1 raised to the minus 4/5, but same argument, 1 raised to any power is 1. So we're going to get, this is 1/5 times 1, which is 1/5. Our linearization, accounting for the letters they picked, which is g, would be g of a plus g prime at a times x minus a, and let me just substitute right below it. G of a was 1, g prime of a was 1/5, x minus a was 0. So this is a very simple linearization equation. It is 1 plus 1/5 x. So that is the approximate straight line curve at x is 0. Now they want us to use that to calculate what is the fifth root of other numbers? But instead of calculating the fifth root on our calculator, we're just going to plug it into this linear equation. So they want us to calculate 0.95. Well, first off, we have to think about this. The equation was 1 plus x. So we want the fifth root of 1 plus x to equal the fifth root of 0.95. So the only way we can get those two to match is if x is negative 0.05. I want to write this and let you think about that. So to get this 1 plus x to equal 0.95, we would have to have x be negative 0.05. And that's what we're going to plug into this linearization equation. So we're going to say, what is the linearization when x is negative 0.05? And we'll get 1 plus 1/5 times negative 0.05. So I would take 0.05 divided by 5, multiply by -1, then add 1, and you should get 0.99. Okay, then the next one they want us to pick is 1.1. So they say the fifth root of 1 plus x should equal the fifth root of 1.1. Well, the only way I can get that 1 plus x to equal 1.1 is if x is positive 0.1. So we need the linearization when x is positive 0.1, which would be 1 plus 1/5 times 0.1, which if you do this out will be 1.02. And that's what goes in these answers here. So, and you can double check this with your calculator. If you take 0.95 raised to the 1/5 power, you will get approximately 0.99. And if you take 1.1 raised to the 1/5 power, you'll get approximately 1.02. But notice we used a much simpler formula. So you could all do, trust me, by hand without a calculator, you could calculate 0.05 divided by 5 and then make it minus and add a 1. And you could all do 1/5, which is just 0.20, times 0.1, which is 0.02, added to 1. You could do that without a calculator. It is really challenging to do a fifth root without a calculator. I'd have to look up the algorithm actually myself to refresh how to do a fifth root of some number. So it's not straightforward. Okay, so that's the first part. Now the last part is they want us to get this picture correct and the linearization. So we have to review a little bit what a fifth root is. A fifth root or any odd root looks like a long elongated S. So this is x raised to any 1 over n power where n is odd. So 1/3, 1/5, 1/7, they all look like this. Now, if we have a plus 1 in there, that plus 1 is going to shift that curve 1 unit left. And it's counterintuitive. Positive numbers go left, negative numbers go right. So this thing is now going to cross not at 0, it's going to cross at -1. So the new curve is going to look like this, but be very similar in shape. Okay, and then A was 0, so we want the tangent line to occur at right at A equal to 0. So let me use the same colors I did before. Use violet for our A value, and then the line we're looking for is right there, that tangent line. And that tangent line is described by the equation we got, which is 1 plus 1/5 x. And we see that it does start, its y-intercept is 1, and then its rise over run is 1 over 5. And the best picture for that is right here. So that looks pretty much like what I drew by just freehanded. Okay, so that would be problem 2. Okay, problem 3. Use a linear approximation or differentials to estimate the given number. Let's do linearization because we've been good at it. So they're taking a number and raising it to the third power. So that means our function is taking a number x and raising it to the third power. And therefore the derivative of this is going to be 3x squared. Now the number they're picking, the number they picked is 1.999, which means the number we should pick is a equal to 2. So we're picking a number really close to the number they picked, 1.99. So let's pick 2, it's easier to use. So let's do f of a, which would equal f of 2, which is 2 cubed, which is 8. Let's try f prime of a, which is the derivative of the function when a is 2, when x is 2, would be 3 times 2 squared, which is 3 times 4, which is 12. Our linearization equation is f of a plus f prime of a times x minus a. F of a was 8, f prime of a was 12, a was 2. So the linearization will become 8 plus 12x, so distribute this 12, minus 24, or the linearization is 12x minus 16. Okay, now we're going to plug in the number they actually used. They didn't use 2, they used 1.99. So we're going to plug 1.99 into this straight line equation. 12 times 1.999 minus 16, and if you do that, you should get 7.988. And again, you can check that on your calculator, type 1.99 raised to the third power, and you will get a number very close to this one. And that would be the answer for problem 3. Okay, problem 4. Same kind of idea, but we've got trig functions now, which always make things more interesting. So we have our function is the sine of x, and therefore we know the derivative right away is cosine of x, and the a value they want is pi over 6. So we're going to just plug all that into the linearization formula. F of a, f prime of a times x minus a. So we're going to get f of a would be sine of pi over 6 plus f prime would be cosine of pi over 6 times x minus pi over 6. Now sine, so I recommend unit circle. If you look at unit circle or type this in your calculator, sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. So now we're out of the trig universe and we have numbers. So L of x would be 1/2, distribute this root 3 over 2. It's going to be minus root 3 pi over 12. So when I distribute root 3 over 2 into pi over 6, the root 3 and pi just go next to each other. They can't combine. But the 2 times the 6 can become 12. Then we have plus root 3 over 2x. And I guess I didn't combine any of these. We just wrote it exactly like that. So this, all of this is the y-intercept. It's just a number. So it has a decimal equivalent. And then this is the slope of that linear approximation line. And you just have to type carefully all that into this answer box and you'll get it if you type it just like I have it there. Okay, so that's problem 4. Okay, 5 is another one where we have to linearize it, draw the original equation, draw the linear approximation, and see how they match up. So our f of x, I'm going to write it a little differently like I did in a previous problem. it's 4 minus x raised to the 1/2 power. Therefore, f prime of x is bring the power down 1/2, leave the parentheses alone, a lot of students forget that. Then it's 1/2 minus 1, then don't forget this step, times the derivative of the parentheses. Derivative of 4 is 0, derivative of minus x is minus 1. So we're going to get this minus 1 is going to multiply into this 1 as part of the 1/2, so it's minus 1 over 2 times the square root of 4 minus x. So the power becomes negative 1/2, so it makes it a radical 4 minus x, but the negative part will flip it into the bottom. Okay, now the a value they picked was 0, so a equals 0. So f of 0 would equal the square root of 4 minus 0, which is the square root of 4, which is 2. F prime of 0 would equal minus 1 over 2 times the square root of 4 minus 0, which is minus 1 over 2 times the square root of 4, which is minus 1 over 2 times 2, which is minus 1 over 4. So, substituting in the linearization equation, f of a plus f prime of a times x minus a, we know f of a was 2. F prime of a was minus 1/4 x minus 0. So the linearization is not too bad. It's 2 minus 1/4 x. And just like before, they want us to calculate different values of x. So they have the square root of 3.9. So they're saying the square root of 4 minus x has to equal the square root of 3.9. Now to get to that value, x would have had to have been 0.1. So just subtract 1/10 from 4 and you'll get 3.9. So let's calculate the linearization when x is 0.1. It would equal 2 minus 1/4 of 0.1. And if you do that, you get approximately, and there's some rounding involved, 1.975. Actually, I think you get that exact value, no rounding needed. Okay, then in the next one, they want root 4 minus x to equal the square root of 3.99, which means x had to have been 0.01. So we find L of 0.01 is 2 minus 1/4 of 0.01, which is going to equal, I also don't believe there's any rounding in this one, 9975. So we didn't have to round, that's equal. And those are the two answers there. And again, you can double check that. Take the square root of 3.9, you'll get approximately 1.975. Take the square root of 3.99 on your calculator, you'll get 1.9975. Okay, now for the picture. So the square root of x, we just saw that one look like this. That's the square root of x, which means the square root of minus x goes like that. This is the square root of minus x. And if we have 4 minus x, that's going to shift this curve we just drew 4 to the left. So we're going to get, actually we have to be careful here. The minus sign is actually going to make this go 4 to the right. So it's counterintuitive. When you put the negative sign in front of the x, now when we add a 4 to it, it actually goes the opposite of what we would anticipate. So a plus 4 in this case is 4 to the right. So now the curve is going to be over here at 4, and it's going to look like this. How can you remember? Well, one easy way to remember is if x is positive 4, you get the square root of 0, which makes the whole thing 0. So that's where we get this 0 point right here, is at positive 4. So then you don't have to think right or left. Just solve, when does that equal 0? Okay, so that green line is the curve, and we're using x to be at a is 0. So again, we're looking at this point here, and we're trying to find this tangent. Watch that. Let me see if I can try that again. We are trying to find the equation of that linearization, and we found it to be 2 minus 1/4 x. So it is up here at, it crosses the y-axis at +2, and its slope is down and to the right, so hence the negative. And that's what it looks like. So we have the correct answer is this one. It starts at 4. It's up here at 2 for the straight line that we're using to approximate. I keep missing that thing. Okay, that would be problem 5, very similar to the one we did before. Okay, problem 6 and beyond are going to introduce a new idea, and that's called a differential. And a differential is this. So it is, if I take a derivative of some y equation, I'm going to get the derivative of the function with respect to x times dx. It's like using chain rule. Normally we don't write that dx there, but now we're going to. Another way to write this is dy dx, which is another form of the derivative, is just f prime of x. In fact, I might have written that way back at the beginning of chapter 3 when we first introduced derivatives. That's one form to write it. So all we did was we moved this x via multiplication over here to the right hand side. Okay, so we have find the differential of each equation. So it says problem 6 part A, y is equal to tangent of the square root of 7t. Well, if I have y is equal to tangent x, the derivative of y would equal secant squared x times dx. So the only difference here is I don't have just x as the argument of tangent, I have the square root of 7t. So we're going to say dy is equal to secant squared of the square root of 7t times the derivative of the square root of 7. So this is chain rule. So we do the derivative of the outside, then we take that times the derivative of the inside, and so in green we're going to get times, this would be 1/2 7t raised to the minus 1/2. So it's really the square root of 7t is equal to 7t to the 1/2 power. The derivative of that is bring the 1/2 down in front like I have, then subtract 1 from the 1/2, which gives you minus 1/2. Then you have to take the derivative of the inside of that times the derivative of 7t would normally be 7. That's how we would have written it before. But now we're going to not write 7. We're not going to just dump the t. It's going to become dt. Okay, so that is the full chain rule on that problem. So putting this all together, dy is equal to, this 7 is going to combine with this 1. This minus 1/2 is going to push this 7t into the denominator with a radical symbol. So we're going to get 7 over 2 square root 7t times secant squared of square root 7t times dt. And I believe, yes, 7 over 2 root times radical 7t, secant squared radical 7t dt. So if you look very carefully, this and this are the same. Okay, that's for part A. For part B, we have y is now 2 minus v squared over 2 plus v squared. Well, for a fraction like this, dy is going to be quotient rule, which says fig minus gif over g squared, where this whole top thing is little f, and this whole bottom thing is little g. So f prime would just be negative 2v, this is the new part, dv. So normally we would have done the derivative of minus v squared is just minus 2v, but now because of these differentials we pick up another term called dv. Basically it's chain rule. Let me show this over here. Minus v squared will become the derivative of the outside says bring the 2 down, subtract 1 from 2, it becomes v to the 1. But then you take the derivative of the inside, which would be v, so it's times dv. So it is chain rule, but we're keeping that dv instead of calling it 1 like we did before. Okay, but that is times, so all that's f prime, times g, which is 2 plus v squared. Then it's minus g prime, which would be, derivative of 2 is 0, derivative of v squared is 2v dv, times f, which is 2 minus v squared. All of that is on top of g squared, 2 plus v squared squared. Okay, let's go all over here. This numerator, when you distribute this 2v dv into those two things, and you distribute this 2v dv into these two things, watch carefully. You're going to get minus 4v dv minus 2, let's see here, v cubed dv. Then this one's going to give us minus sign out front, so minus 4 v dv, and minus of a minus would be plus 2 v cubed dv, all over 2 plus v squared squared. Now if you look very carefully, you got minus 2v cubed dv, and we have plus 2v cubed dv. Those are going to cancel, and these are exactly the same, so they're going to combine into negative 8v dv over 2 plus v squared squared. I believe that is it. Yes. Okay, so we used chain rule and quotient rule in these two problems. Very good review, and a trig function that's kind of not that common, tangent. So we saw a couple good examples here of stuff we have seen before, but never hurts to practice it more. It's problem 6. Problem 7. Okay, find the differential. We have y equal to ex over 2, and we recall if y equals e to some function of x, y prime is the derivative of that function times e to that function. So we always get e to that function back out, but in front of it we put the derivative of that function. So dy would be the derivative of 1/2 x, which is 1/2 dx, e to the x over 2. So notice what happens in a derivative of e is this stays exactly the same, but this is the derivative of this. So 1/2 x, derivative of that will be 1/2 dx. Okay, so I think I just rearranged the order a little bit. So we say this is dy is 1/2 e to the x over 2 dx. We usually like to write dx last, so that's how I wrote it there. Okay, now it says, imagine, that was part A. For part B it says, imagine x equals 0 and dx is equal to 0.01. dx is like an error. It's like an error in the measurement. So if we have an error of 0.01, when x is 0, how much total error will be in this measurement, let's say. In fact, that's what we'll do in a few problems here. We'll do real problems where we have these error terms, and we see how much error gets picked up, because the inherent nature of our measuring tools just have error in them. We can't make perfect tools. perfect scales. Okay, so dy is equal to 1/2 e, x is 0, so it's 0 over 2, times 0.01. Well, this is e to the 0, 0 over 2 is 0. Anything to the 0 power is 1, so we get e to the 0 is 1 times 0.01. Well, this is just 1/2 times 1, which is 0.5, times 0.01, which will equal 0.005. Okay, so in that one, they just want us to substitute in some numbers for this particular equation that we derived for problem 7. Okay, in problem 8, they want us to do 2 different equations and see how close they are. So there's another way we can do a differential, and that's by saying a change in y, and that is equal to the function evaluated when x is increased by a small amount minus the original function, f of x. Just make sure I got the equation right. Yes, I do. Okay, so they give us our function is y is equal to x squared minus 7x. And they tell us calculate this when x is 6 and when the change in x, the small increase to x, is 0.5. So the change in y is going to equal the function when x is 6 and the change in x is 0.5 minus the function evaluated when x is 6. So we're going to get, this is really 6.5 plugged into the original function. The original function is x squared, so it's 6.5 squared minus 7 times x, which is 6.5. All of that matches this. Okay, then it's minus f of 6, which would just be 6 squared minus 7 times 6. And if you do this, did I write down the intermediate values? I did. Okay, so we have this would be, if you do it right on your calculator, negative 3.25 minus this one will be negative 6, double negative, this whole thing will equal 2.75. Okay, so that goes right here. Okay, so that's yet another method to calculate a small change in a y value by changing your x value by a small amount. So it's kind of like, how much did my function change based on a small change in x? Then the second part, they want us to use differentials like we just did in the previous couple problems. So let's write it again, what we had. Y is equal to x squared minus 7x when x is 6, and now when dx is 0.5. So notice that this dx and we call this del x, are the same thing. So those are both 0.5. But we don't need del x, we have dx. So we do dy would be 2x dx minus 7 dx. And when we plug in what we know x is 6, we know dx is 0.5, minus 7 times dx, which is 0.5. We will get, this is half of 12, which is 6, and this is half of 7, which is 3.5. So it equals 2.5. And those are pretty close. So 2.5 and 2.75 calculated 2 different ways. They're interpreting the same thing. They're pretty close to each other. Now the picture for this is this one right here. So to find this, we have a parabola where the a value is 1 and the b value is minus 7. This is a, this is b. And to find the vertex, which we call h, of this parabola, you take minus b over 2a, which would be minus 7 over 2 times 1, which would be 7/2, which is 3.5. So this vertex has to be at, did I miss a negative here? I did not miss a negative, I circled the wrong answer. I got the answer right, but I circled the wrong one. The correct answer is over here, top left. So the vertex should be at 3.5, which is approximately right there, 3.5. To get this value, the y value for this vertex, so we call this h, we call that k. To find that, you have to plug h into the original parabola equation. So you would say k is equal to 3.5 squared minus 7 times 3.5. And if you do that, you will get negative 12.25, which looks exactly like where we have it, negative 12 and a little bit more. Okay, so that identifies the vertex of the parabola, which is going to allow you to eliminate both of these down here. And then the only other part is to find the equation for the slope of this tangent line, which is governed by these del y and del x's. So at x is 6, so we want to calculate when x is 6. So from here, del x says we go over by 0.5, and dy or del y is either 2.5 or 2.75. So this distance, and you can see these tick marks go by a half, this is 0.5 exactly, and then this goes up by almost 3. So that's how you can tell that that purple line is correct for this particular problem. Problem 8. Okay, problem 9. Oh, let's look back at that one more time. The only reason I know between this one and this one is del y is slightly longer than dy, which is true. Del y is slightly bigger than dy. Where in this one, they drew well, they have dx too, that's completely wrong. So dx is definitely not vertical, so we could eliminate that, but also they drew it longer than del y. So a couple things wrong there. Okay, now we can go to 9. So 9 says the edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.5 centimeters. Use differentials to estimate the maximum possible error. So we have a cube. Its dimensions are x, x, and x, which means its volume is length times width times height, which is x to the third. We want to find the differential of the volume. That would be 3x squared times dx, based on what we've just been working on. They say x in this problem is 30 centimeters, and dx, the error, is 0.5 centimeters. So the first thing we're going to find is the maximum differential volume, which would be 3 times 30 centimeters squared times 0.5 centimeters. And if you do this, at least for my numbers, this is 900 times 3, which is 2700 times 0.5, which is 1350 centimeters cubed, because we have 2 centimeters here and then another one here, that's 3. So that is the maximum differential volume or possible error. Now relative error, it's in the name, it's relative to a reference. The reference is the volume V. So relative error is the differential volume divided by the original volume. Well, differential volume is 3x squared times dx, and the volume equation was x cubed. So we get all 2 x's on top to cancel with 2 x's on the bottom. So we get 3 times dx over x, and we know dx is 0.5, and we know x is 30 centimeters. That's the only one that has units on it. Actually, this one has units too, centimeters. So we get the centimeters to cancel, and we get 3 times 0.5 over 30. So we get the relative error is 0.05. And that has no units because the units cancel. Okay, so 0.05. And then the percentage error, so the percentage error is just equal to the relative error times 100%. So we take 0.05 times 100%, jump the decimal 2 to the right, add a percent sign, it's 5%. Okay, so that would be the percentage error, about 5% error with that much when we have 0.5 centimeter error in one dimension. So notice each dimension could be off by as much as half a centimeter. So we're saying the side is 30 centimeters. Well, maybe it's actually 30.5, or maybe it's 29.5. Well, if all of them are off, let's say all of them are off by half smaller, so 29.5, 29.5, 29.5. That's a much different size than if they're all off on the bigger side, 30.5 times 30.5 times 30.5. So that's where you can get into these different errors with measurements, because like I said before, all measurements have an inherent amount of error in them. Okay, then the second part is going to look at surface area of the box. Oh, I wish I didn't erase it. Draw it again. Oh, I made it much worse this time. Dang it. Okay, so it looks something like this. Just make it worse and worse now. When in doubt, just make your lines wider. Okay, there's our cube. Surface area, imagine any one of these sides. They're x in one dimension, x in the other. So one side has a total area, let's use color. Any one side has a total surface area of x squared. And we just have to know that in a cube there are 6 sides. So one side is x squared times 6 of them. The surface area is 6x squared. Just like before, we're going to find differential surface area, which would be 12x times dx. But now we have the same numbers. We have x was again 30 centimeters. Dx was again 0.5, half a centimeter. So the maximum differential surface area is 180. Now notice, area only has units of something squared. So this is centimeters squared. Right there. Now relative area is going to be the same thing. It's differential surface area divided by surface area. So it's 12x dx divided by 6x squared. The 12 in the x on top will cancel with 1x on bottom. The 12 will absorb the 6 and become a 2. So we have 2 dx on top, and we have just x on the bottom. So this is 2 times half a centimeter divided by 30 centimeters. And if you do that, you'll get 0.0333, and that repeats. And it's unitless because the centimeters on top cancel the centimeters on bottom. Okay. And then percentage error would just equal that 2 decimals to the right, so it's 3.333 repeating percent. So that would be the percentage error for the surface area. So notice your percentage error is not as large with this because your error only shows up in the multiplication of your x times your x. When you add 6 of them, it doesn't increase the error more. So in 2 dimensions, you have less error than in 3 dimensions because that error is being multiplied 3 times versus the error being multiplied twice for a 2-dimensional idea. Okay, and that's for problem 9. Okay, problem 10, they give us a curve, and now the tricky part of this curve is not the function, it is the curve of the derivative of the function. So it says, suppose that the only information we have about a function f is that f of 1 equals 4. So f of 1 equals 4. But then they give us the derivative of this, so f prime at 1 equals what? So notice we have to have a equal 1, otherwise we can't really do this problem. So if a is 1, then f prime of 1 would be the value at this point when x is 1. The y value, if you read it off here, is 2. So f prime of 1 is 2. Now we know the linearization of any function is f of a plus f prime of a times x minus a. And we know f of a was given to be 4. F prime of a we read off the chart was 2. And we know that they picked a as 1. So the linearization of this is another pretty simple one. 4 plus 2x minus 2, which simplifies into 2 plus 2x. And they don't even want the linearization. We need it for the next part. So they say, okay, use a linear approximation to estimate f of 0.99 and f of 0.101. Now notice, in this problem, we do not have to do any subtracting or anything. So if their a is 1, this is really close to a. There's no subtraction or anything needed to get the x value. We're going to say these are close to a. So what they actually want us to do is just use those numbers directly. So the linearization when x is 0.99 would equal 2 plus 2 times 0.99, which would be, if you do that out, 3.98. Then they want us to calculate 1.01. So it's 2 plus 2 times 1.01. And that's going to equal 4.02 when you multiply that out. Okay, so that's the two answers here and here. Now it says, are your estimates in part A too large or too small? Well, since if you look at this curve of this tangent line, or the derivative, it's getting increasingly, the values are getting increasingly smaller. Okay, and they're positive, so they're above 0, but they're getting smaller. So because they're positive and they're becoming less steep, that means our tangent line is above the curve at f, therefore our estimates are too large. Okay, so if you kind of reason that out, you can see that our tangent line would lie above our original curve. Okay, and that will complete section 3.10.